Now moving to next example. Example 6. Let x1, x2, so on be a sequence of independent random variables each having probability mass function probability of xi is equal to 1, that is same as probability of xi takes a value minus 1, the probability is 1 by 2. This is valid for that means it is a sequence of IID random variables and they are discrete type. Define m suffix k as the sum of first k xi random variables. So, this running index is k is equal to 1, 2 and so on. So, we are defining a sequence of a random variable m k by summing first k xi random variables. For a fixed integer n, we define another sequence of random variable that is denoted by w superscript n of t, that is nothing but 1 divided by square root of n m suffix n times t. This is for all t greater than or equal to 0 such that n times t is an integer. So, we are defining another sequence of random variables w superscript n of t, that is 1 divided by square root of n times mn of t, where n of t is an integer. So, this is valid for all t greater than or equal to 0. If you find out the mean and variance for the difference of the random variable of n of t minus w n of s for 0 less than or equal to s less than or equal to t, this quantity will be 0. That means w n of t is 1 divided by square root of n m n of t, and the way we define the m n of t, that is a summation of xi's, and the probability of xi is equal to 1 and the probability of x is equal to minus 1 is 1 by 2. Therefore, the mean of xi's are going to be 0. Because of that, the expectation of or mean of w n of t minus w n of s, that is equal to 0. Also, if you evaluate the variance of w n of t minus w n of s by finding first variance of xi's, using that you find out the variance of m n of t, then find out the variance of w n of t minus w n of s, that is going to be t minus s. It need a calculation of expectation of xi square, then using expectation of xi square and the expectation of xi's, you can find out the variance of xi's. Using variance of xi's, you can find out the variance of Wn of t, then you find out the variance of Wn of t minus Wn of s. By using mean and variance for fix t greater than or equal to 0 as n tends to infinity, we can conclude Wn of t tends to a random variable x, and this convergence takes place in distribution. Using CLT, one can conclude Wn of t converges to the random variable x and the convergence in distribution, where x is normal distribution with the mean 0 and the variance t. Using a central limit theorem, one can prove Wn of t converges to x in distribution, where x is a normal distribution with the mean 0 and the variance t. This result is very useful in Brownian motion, and this same problem will be discussed in detail when we are discussing the model of Brownian motion.